Hello students, this is Anjana from Computer Science Department. In this class, we are going to discuss about the next part of the introduction to number theory. These are the concepts that we are going to discuss here. Factorization, Chinese remainder theorem, quadratic congruence, exponentiation, and about the logarithms. Go for the next slide. So we have already discussed about the prime numbers. Here the prime numbers are the only we are having the divisors of 1 and self that they can't be written as a product of the numbers. Suppose for example we can say what is a prime number here. A prime number is anything which can be divisible by itself and it cannot be divisible by the another number, so we can say that one as a prime number. So here in this slide we are saying about the prime numbers here. These are the prime numbers from the up to infinite, up to in the number system up to infinite. The number which is divisible by itself, the number which is divisible by itself and it can't be divisible by another number. Suppose if we have taken the example of 2, 2 is a number, it is divisible by 2 itself. It can't be divisible by any other number like 3, 4, just like that. Yes or no? Next, 5. 3 is also just like that. 3 is divisible by 3 itself and it can't be divisible by any other number. So if we have taken the example of 4 here, the 4 can be divisible by 1, 2 and 4 also. So we can't say it as a prime number. Okay, 4 is divisible by instead of 4 also it is divisible by other numbers. So we can't say it as a prime number. And here if we have taken the example of 5, 5 if we have taken the 5 is also divisible by 5 itself and it can't be divisible by any other number. So we can say 5 as a prime number. From this we can say these are the list of the prime numbers here. The prime number have only divisors of 1 and self, they can't be written as a product of the numbers. So we can say 1 is prime. So but is generally we can't say it is not of interest. Suppose if we have taken the example 2, 3, 5 and 7, these are the prime numbers. So from this we can say that 4, 6, 8, 10 are not prime numbers. Why? Because these two are not prime numbers. Why? Because here 2, 3, 5, 7 are divisible by the by themselves itself, but the numbers 4, 6, 8, 9, 10, these numbers are, so see if you have taken the example of 4, 4 is divisible by 2 itself, 6 is divisible by 2, 3 and 6, 8 divisible by 2, 4, 8, 9 divisible by 3, 3, 9, just like that. 10 is divisible by 2, 5. So these numbers are divisible by themselves. These numbers are divisible by themselves and these are not divisible by these are themselves and other numbers also. Here if you have taken the example of these prime numbers 2, 3, 5 and 7, these numbers are divisible by themselves itself. So this is about the example. So we can say the prime numbers are the central to the number theory. So these are the list of the prime numbers that is less than 200. See if you have taken the example of infinite, these are not the example, we can't say about that. But if you have taken less than 200, these are the examples of the prime numbers. See, this is a list of the prime numbers that is less than 200. 2, 3, 5, 7, 11, 13, just like that. Go for the next slide. This is a prime factorization. This is a prime factorization. To factor a number n, if you have taken the example of the factorization, to factor a number n, it is to write a product of the numbers. That is n is equal to a, b, c. You have to note that factoring a number is relatively hard compared to the multiplying the factors together to generate the number. Suppose the prime factorization of a number n is when it is written as a product of the primes. See, when we can say it is a product of primes, that we can say that one as a factorization. See, if you have observed 91, it is a example, it is a product of It is the product of factors. See, 7 is a prime number and 13 is also a prime number. If you have multiplied these two numbers, so we can say this as a product of prime numbers. Okay. If you have observed this one as an example, 3600, we have taken these prime numbers, that is 2 power 4, 3 square into 5 square. That is 2 is a prime number, 3 is a prime number, and 5 is also a prime number. So we can say this one as a product of primes. So we can say it as a prime factorization. To factor a number n is to write as a product of the numbers. We can say n as n into a, b, c. So we can say that note that factoring the number is relatively hard compared to the multiplying the factors together to generate a number. So the prime factorization of a number n is when it is written as a product of primes. We can say it as a product of primes. See, this is the example. 91 is equal to 7 into 13. This is a prime. 7 is a prime number, 13 is a prime number, so we can say it as a product of prime. So 3600, 2 power 4, 2 is a prime number, 3 is a prime number, and 5 is a prime number. So this one is also a product of the primes. Now go for the next slide. See, if you have taken this relatively prime numbers and greatest common decider, two numbers a comma b relatively prime if we have no common divisors. See, when two numbers are relatively prime, when we can say that the two numbers are relatively prime, when the two numbers are not having the common divisor, so we can say it as a apart from one. Okay, one is any number is always divisible by one, but apart from one, if no other two numbers have having the common divisors, so we can say it as a relatively prime numbers. Okay, suppose example 8 and 15 are the relatively prime numbers, since the factors of 8, see, 8 and 5 are the relatively prime numbers. How we can say these are relatively prime numbers? Why? Because the factors of 8 are 1, 2, 4, 8. That is 8 divisible by 1, 2, 4 and 8. And 15 are the suppose if you have taken the example of 15, the prime number, the factors of this one is 15 is divisible by 1, 3, 5, 15, just like that. Here the common factor is only 1. Apart from 1, if there are more than one common divisors, we can say those are not relatively prime. If the common factor is only 1, we can say that one as a relatively prime. So from this conversely, we can determine that we can easily determine the greatest common divisor by comparing the prime factorization by using the least powers. See, from this we can find out the greatest common divisor. So suppose if you have taken the example of 300, so 2 power 1 into 3 power 1 into 5 square. 5 square means 25. 25 6 25 into 6, just like that they have written like that. Suppose if you have taken the 18, 2 power 1, 2 power 1 means 3 square means 9. 9 into 2, 18. Okay. So here the greatest common divisor. See here the common Here the common factors are 2 power 1 into 3 power 1 into 5 power 0. So here the result that we got is 6. So here the GCD of these two numbers is 6. Here you observed how we are going to find out the GCD of a number or two numbers. First of all, you have to find out the prime factorization for that first number, and next you have to find out the prime factorization of the second number. Then you have to compare the both prime factorizations there. 2 power 1, 3 power 1 into 5 square, just like that. If you have observed that here the common factors are 2 power 1 into 3 power 1. So here the greatest common divisor for these two numbers is 6. See, this is the Fermat's theorem. that is implies that a power p minus, this is a theorem, the main rule for this theorem, a power p minus 1 mod p is equal to 1. Here p is a prime and GCD of a comma p is equal to 1. Okay, if we have performed the greatest common divisor of a comma p, then the greatest common divisor of a comma p is, so we can also known as the Fermat's, we can also say this one as a Fermat's little theorem. So this one is a used in the public key and primality testing. So basically all this theorem is all whatever the theorems that we are using in this cryptography. Just these theorems are just for you, just to use the public key and primality. In order to generate the public key and to perform the primality testing, we are going to use this Fermat's theorem. Okay? See, this is about the Euler Totient function. See, whenever you are going to perform the arithmetic operations of modulo n, you have to keep focus on the complete set of residues. That is, if you are having some sets, we are having set of numbers that is 0 to n minus 1, not about 0 to 1, 0 to n minus 1. From for that 0 to n minus 1 set of residues, you have to perform the arithmetic modulo operation. When doing the arithmetic modulo of n, the complete set of residues is 0 to n minus 1. Here the reduced set of residues is those numbers which are relatively prime to n. See, for example, if you have taken the set of numbers, that is n, if n is equal to 10, you have to take the numbers from 0 to 9, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, here the reduced set of residues is 1, 3, 7 and 9. The number of elements here, if you have observed this, the number of elements the reduced set of residues is called. So here, what are the number of numbers here? What are the numbers that we have taken here? 1, 3, 7, 9. That is the set. This set of 0 to 9 is reduced from the another set called 1, 3, 7 and 9. So the number of elements in the reduced set of residues, we can say it as a Euler Totient function. We can define it as by using the phi of n. So whenever you are going to perform the arithmetic modulo operation n, you have to complete the set of residues, that is 0 to n minus 1. Here the reduced set of residues is those numbers which are relatively prime to n. Example, for n is equal to 10, if you have taken the example for n is equal to 10, here the complete set of residues is 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Here the reduced set of residues is 1, 3, 7 and 9. Here, so the number of elements in the reduced set of residues is called Euler Totient function. Okay. Here, if you want to compute the phi of n, you need to count the number of elements to be executed. How many numbers that are used, that we are going to use? We have to count the numbers first, number of elements first that are going to execute there. So in general, if you are going to perform the prime factorization, but for p of prime, that is phi of p is equal to p minus 1. So for p of prime is the prime of phi of p is equal to p minus 1. For p dot q, p comma q are prime. So phi of p dot q is equal to p minus 1 into q minus 1. So if you have taken the example, phi of 37 is equal to 36, just like that you can write phi of 21 is equal to 3 minus 1 into 7 minus 1, that is 2 into 6 is equal to 12. Just like that we are going to solve the problem here. So see, if you have observed this n as an example, to compute the phi of n, you need to count the number of elements that we are going to be executed. And in general, the need of prime factorization is whenever you are going to use a prime, but p of prime is equal to phi of p, that is equal to p minus 1. For p dot q of p comma q of prime, so p dot q is equal to p minus 1 into q minus 1. If you have applied that rule, Phi of 37 is equal to 36. Then phi of 21 is equal to 3 minus 1 into 7 minus 1. That is 2 into 6 is equal to 12. See, this is about the Euler's theorem. This is a generalization of the Fermat's theorem. So this is the formula for that. A power phi of n modular operation of n is equal to 1. If you have performed the GCD operation of a comma n, it should be 1. So we have already seen about the GCD, that how we are going to perform the GCD operation there. So if we have taken the example, a is equal to 3, n is equal to 10, phi of 10 is equal to 4. Hence 3 power 4 is equal to 81, that is 1 modulo 10. Here a is equal to 2, and if you have taken the value of n is equal to 11, then phi of 11 is equal to 10. Hence 2 power 10 is equal to 1024, that is 1 modulo 11. That is the operation that we are going to get here. So this is a Euler's theorem. We can say this one as generalization of the Fermat's theorem. Suppose if a of phi of n is equal to modulus of n is equal to 1, where GCD is equal to a of a comma n, that is equal to the value should be equal to 1. So if you have taken the example, a is equal to 3, n is equal to 10. So phi of 10 is equal to 4. Hence 3 power 4 is equal to 81. That is 1 modulo 10. And a is equal to 2, n is equal to 11. Phi of 11 is equal to 10. Hence 2 power 10 is equal to 1024. That is 1 modulo 11. This is a generalization of a Fermat's theorem. So how we are going to perform the primality testing? See, often need to find the large prime numbers. Traditionally, we are going to see using the trial version. That is, we are going to divide all the numbers, that is prime numbers, in turn less than the square root of the number. So it works only. It only works for the small numbers. That is, alternatively, we can use the statistical primality test based upon the properties of the primes. So for all which the prime numbers satisfy the property, but some composite numbers called pseudo primes, it is also going to satisfy the property. See, here whenever it is going to, it is often need to find the large numbers. If you are going to find the primal, see, it is a traditionally see by using the trial version. See, if whenever you are dividing all the numbers by using the primes, in turn it should be less than the square root of that number. So whenever you are going to use the square root of that number, it only works for the small number. So alternatively, we can use the statistical primality test based upon the property of the primes, for which all the prime numbers satisfy this property. But some prime composite numbers called pseudo primes, it also satisfy this property. So if you observe this primality testing, it is alternatively you can use the statistical primality upon the property of the primes. So this is a Rabin algorithm. It is just based upon the primality theorem. So the algorithm is test. If you have to perform the test of n, that is how many number of times that you are going to perform, you can perform there. Then for that the theorem is, if you have to find out the integers k, that is q comma k is greater than 0 and q should be odd, so that n minus 1 is equal to 2 power k of q. So that from this we can select a random number a, that is 1 less than a less than n minus 1. So if a power q modulo of n is equal to 1, then we can return it may be prime. We can return the value, it may be prime. For j is equal to 0 to k minus 1, that is you have to perform the loop operation there here up to k minus, k should be greater than 0. K is the limit, that what is the limit that we are going to take there. So if a power q is equal to a modulus of n is equal to 1, then you have to return it should be written that it may be prime. So for j is equal to 0 to k minus 1, for j is equal to 0 to k minus 1, you have to do the operation like, if a power if a square j q modulus of n is equal to n minus 1, so then it should be written like, it should be prime. we can finally we can otherwise we can return it should be a component number. It should be written like it is a component number. Understand? If you applied that, we can say that it is a prime. Otherwise we can say that it is a composite number. Okay. See, these are the probabilistic considerations. Suppose if a Miller-Rabin theorem, if it is it is going to return the composite number, then we can say it is not definitely prime. Okay, so we need not to bother about that. Otherwise, it is a prime, or otherwise we can say it as prime or pseudo prime. Okay, if you are having the chance to detect it one as a pseudo prime, it should be less than 1 by 4. Hence, if you are going to repeat the test with the different random, and we are having the chance and it is a prime after the t-test is PR is equal to n prime after t-test. Example, if you have taken the example for t is equal to 10, this the probability is greater than 0.9999, just like this is the theorem that suppose if it is a consideration, what is the probabilistic consideration that we are going to get? If Miller-Rabin returns composite, the number is definite. That number should not be definitely a prime number. Otherwise, otherwise we can say it as a prime or pseudo prime. It is having the chance it detects a pseudo prime is less than 1 by 4. Hence, if repeat the test with different random, uh, then it is having the chance it is a prime after t-test. That is PR is equal to n prime after t-test 1 minus 4 power minus t. For example, for t is equal to 10, this is the probability is greater than 0.9999, just like that it is going to get there. So we can say it is having the chance to detect a pseudo prime less than 1/4. So how we are going to distribute the prime distribution? See, the prime number theorem states that the prime occur roughly for every L of n comma n integers. That is, if you are going to consider this prime numbers, it is going to get like that. See, if you have taken this example, since we can immediately ignore if it is a even and if it is a multiple of 5, definitely we can ignore that. But in practice, we can only need the test up to 0.4 L of n, that is number of size before locate a prime. Note this only the average, sometimes the primes are always close together and other times it is quite far apart. So from this we can say that it is not immediately ignore events and the multiples of 5 in practice and only need to test. So from this we can note this is only the average. Sometimes the primes are close together and other times it is quite far. Okay, if you have observed the difference, this is the basic difference here. Sometimes it is close together, sometimes it is quite far. See, this is about the Chinese remainder theorem. We have to we have to speed these things up to the n modulo computations. When you are performing the modulo operations on the product of a numbers, example, modulus of m is equal to m1, m2, m3 and so on up to mk. The Chinese remainder theorem, let us work with each modulo mi separately. It is going to work with each modulo mi separately. So since the computational cost is proportional to the size, here the computational cost is directly proportional to the size. This is faster than working in the full modules of, this is very faster than working in the full modules m. So from this we can say that it can be used to speed up the modular computations and it can be used for working modulo a product of the numbers. So if you have taken the example of modulus of m is equal to m1, m2 and so on mk. So from this the Chinese remainder theorem, let us work with each modulo mi separately. So from this we can say that the computational cost is directly proportional to the size. So this is faster than working in the full modules M. See, this is the Chinese remainder theorem. We can implement it in the several to compute the A modulus M. and firstly compute all. So AI modulus mi separately, then we can combine the results to get the answer by using that. A is equal to sigma of I is equal to 1 to k, that is we have to perform the sum operations to AI into A1 C1 plus A2 C2 plus A3 C3 plus A4 C4 and so on, AN AK into CK. Just like that you have to perform the sigma sum operation. For that you have to perform the modulus operation of M, where C comma I is equal to M of I into M of I power minus 1 modulus Mi, where for 1 less than or equal to I less than or equal to K. Okay, this is how we are going to perform here. The operation to compute this A modulus M, you can firstly compute all AI mod Mi separately, and then you have to combine. First of all you have to compute AI mod Mi. Okay, then you have to combine all the results to get the answer. Okay, by using this formula. Okay, so these are the primitive roots here. From the Euler's theorem, we can say that a of phi comma phi of n is n mod n is equal to 1. So if you consider a power m mod n is equal to 1, then GCD of a comma n is equal to 1. So it must be exist for m is equal to phi of n, but maybe smaller. Once powers reach m, we can repeat, definitely the cycle will repeat. If smallest is m is equal to phi of n, then a is called a primitive root. So if p is a prime, then successive powers of generate the group mod p. These are the useful, but relatively these are useful, but it is relatively very hard to find. So this is about the discrete logarithms. So the inverse problems and the exponentiation is to find the why you are going for the discrete algorithms is to find out the inverse problems and exponentiations of a number of modulus operation p. So that is if you are going to find the value of x, where a power x is equal to b mod p, we can written as x is equal to log log of b to the a mod p, or x is equal to d of a comma p of b. So if a is a primitive root, then always exists, otherwise it may not exist. So for x is equal to log 4 to the base 3 mod 13, we can say x of st 3 power x is equal to 4 mod 13. We doesn't have, for this we need not to calculate. This is not a particular answer here. If you have taken this example, x of x is equal to log 3 to the base 2 of mod 13 is equal to 4 by trying the successive powers. So while exponentiation is relatively easy, finding the discrete algorithms, and it is generally a hard problem. Okay, this is about the induction number theory of part 2. Then we will continue in the next class. Thank you.